Welcome back. In the last lecture, we are trying to prove Weyl's criterion for equidistributed sequence. So, we are halfway through our proof on one side. That was what we wanted to prove, that if limit n goes to infinity 1 over n equal to 1 to n e to the power 2 pi I k xi n, this is equal to 0 for all 0 non-zero integer, then the sequence xi n is equidistributed. So, in order to do that, what essentially what we have observed, to show something is equidistributed, what we need to show, need to prove 1 over n summation n equal to 1 to n chi of a b for a subinterval a b in 0 1, this goes to 0 to 1 chi of a b t dt. This is what we want to prove, and what we have achieved? We have achieved that for every one periodic continuous function f, we proved limit n goes to infinity 1 over n summation over n from 1 to n f of xi n, this is equal to 0 to 1 f t dt. Now, from the continuous function, we would like to go to the indicator function of 0 1 step function of 0. So, pictorially let us look like this. I have a b. So, indicator function of 0 1 is a b is this, and then 0 here, and outside a 0 here and 1 here. That is what the indicator function of this. Now, what I can do is that, depending on my a, where is the position of a, I can find, because a is strictly bigger than 0, therefore, I can find some epsilon where this a minus epsilon, this is a minus epsilon, and b plus epsilon, this is going to lie inside the interval 0 1. So, now I will take a continuous function which is this, which takes the value at value 1 in the interval a b, and it drops such that, as we have seen it in earlier occasion, this area of this is of course is this two triangle, the ear triangle, the area is going to be epsilon plus epsilon, which is 2 epsilon. That is the maximum what I will get. So, now, so define, so we can find epsilon positive such that a minus epsilon is strictly positive and b plus epsilon is strictly less than 1. That I can always get. Now, if I take from, or rather this epsilon naught. So, any epsilon less than epsilon naught, we have a minus epsilon and b plus epsilon, this is in 0 1. So, now define f epsilon plus this is equal to of x is equal to 1 if x belongs to a b, and 0 if x does not belongs to a minus epsilon and b plus epsilon. Outside this is 0, that is what I am considering, and this is a continuous function and continuous linear on the interval b a minus epsilon to a union b to b plus epsilon. So, as you can see that if I take the integral 0 to 1 of this continuous function t dt, then this is going to be a minus epsilon to a plus a to b plus b to b plus epsilon, and here in this is f epsilon plus f epsilon plus f epsilon plus. So, here this is equal to b minus a plus this one would be less than definitely 1 because it is linear. So, the entire thing is less than epsilon, and this one is also. So, this is equal to b minus a plus 2 epsilon. Similarly, in a bigger picture, this is 0 1, this is my a b. So, now what I will do is, so this is my a minus epsilon, and then this is a plus epsilon, this is b minus epsilon. So, I will take 1 over here and then I will drop it linear. Let us say this is b minus 3 by 2 epsilon, then this is a plus 3 epsilon by 2, and it will take the value 1 in between, and after this is 0. So, this f epsilon minus of 1 t, this is equal to 1 on a plus 3 epsilon by 2, b minus 3 epsilon by 2, 0 if t does not belongs to a minus a plus epsilon to b minus epsilon, and linear. Then clearly in this case integral 0 to 1 f epsilon minus of t dt, this is equal to b minus of a minus of 2 epsilon. So, by the construction what we can see is that f epsilon minus of t, this is always lesser equal to indicator function of a b of t, because on a plus 3 epsilon by 2 to b minus 3 epsilon by 2, it is taking the same value. Now, indicator function of a b is goes up to takes the value 1 up to a b. Now, you are chopping it off, which is less than 1. So, this is true for all t, which again is lesser equal to f epsilon plus of t, because there you are putting the ear outside a b, small to small ear there. So, this is always true. Hence, what do we get from this? So, therefore, f epsilon minus of this xi n is lesser equal to chi of a b of xi n which is lesser equal to f epsilon plus of xi n. Therefore, the summation over n from 1 to n is less or equal to summation over 1 to n is less or equal to summation 1 to n. Therefore, if I divide 1 by n, 1 by n, 1 by n, remember that the both f epsilon minus and f epsilon plus, they are continuous function. So, this is going to be 0 to this of course is going to be 0 to 1 f epsilon minus of t dt. This is going to goes to 0 to 1 f epsilon plus t dt. Now, this we have seen that this is b minus of a plus 2 epsilon, this is b minus of a minus 2 epsilon. Therefore, for every epsilon for large n, we are going to get that this. So, now this is going to be sandwiched by this. So, when this goes to something like this will converge, let us say it converges to some limit alpha, then this alpha is less or equal to b minus epsilon minus 2 epsilon and b minus epsilon plus 2 epsilon, and this is true for every very arbitrarily small epsilon. Therefore, thus limit n goes to infinity, true for all arbitrary small epsilon. And that is what exactly what we wanted to prove, and this shows that this will imply that xi n is equidistributed. Okay. So, now we would like to prove the converse of Weyl criterion. So, the converse, it says the converse of Weyl what does it say? If for all non-zero integers k, limit n goes to infinity 1 by if no. So, if xi n is equidistributed, then limit n goes to infinity 1 by n k xi n, this is equal to 0 for all non-zero integer k. Okay. So, now this statement xi n is equidistributed means what? This we have seen that this implies that for every subinterval a b 0 1, what limit n goes to infinity 1 over n in how many xi are there in the interval a b. This is the cardinality, and then this is equal to b minus of a. that means this is integral 0 to 1 indicator function of a b. This is given to us. Now, what we will prove that this happens. Now, if we can prove, if we can replace the indicator function by a continuous function, then obviously in particular we will get this is going to be a continuous function. Therefore, so now we had been given with, let us say, a continuous function. This is in fact the argument goes for every Riemann integrable function. Now, if I have a continuous function and if I want to look at the integral of that, then look at the Riemann prescription, how we are doing. We are taking the lower sum and the upper sum, and where it converges, then that is what the integral is. So, that means if I take f l to be for certain thing, if I am dividing it by this f l of x, this is some m star and chi of I k f of x k, let us say from 1 to n, and rather this is m small n f, where m f k, or rather m k, let us just put it, that is much more simpler. M k is infimum, or rather in this case minimum, because we are doing the continuous function f of x, such that x belongs to I k. Now, for this f l, now if I look at some m, now this f l of x, this is lesser equal to f of x. Now, what one can do is that this then one of, similarly, if I take the u upper sum is k equal to 1 to n, I divide a b into the n equal parts with the 1 by n, and then this is m k f indicator function I k. Now, if I take this integral, then this is integral of f l is a lower sum, this integral of f u is upper sum, and now the f l, if I replace this, this is true for every subinterval a b. Therefore, if I replace it in the 0 1 interval 0 to this criterion, this is true for, so therefore, limit n goes to infinity 1 over n, summation over n from 1 to n f l of xi n, this is going to converge into the Riemann sum. This is going to n goes to infinity. This is going to get me the integral of this, and the integral of this is nothing but the Riemann integral of this. Now, f l of xi n is lesser equal to f of xi n is lesser equal to f u of xi n. Hence, this sum which is lesser, if we take out the limit here, this is lesser or equal to 1 by n summation over n equal to 1 to n f of xi n, which is 1 by n summation over n to 1 to n f u of xi n. Now, this side converges to integral of 0 to 1 f t dt, and this converges to 0 to 1 f t dt. So, therefore, this the middle one has no other choice but to converge to 0 to 1 integral 0 to 1 f t dt. So, therefore, in particular if we choose our f to be e to the power 2 pi I k t, then by the previous observation we have got summation over 1 by n equal to 1 to n e to the power 2 pi I k xi n. This is going to converge to 0 to 1 e to the power 2 pi I k t dt. Now, k is a non-zero quantity. So, once k is a non-zero quantity, this we have seen many times that this is equal to 0. So, this is one application of the Fourier series. What we have seen is this is called the Weyl equidistribution theorem. That is what the Weyl's criterion is known as, and which has many applications. Thank you.